large number of orbitals are possible in an atom. Qualitatively, we can say that these orbitals can be differentiated by their size, shape, and orientation. An orbital of smaller size, it means that this orbital is near to the nucleus. That means finding of the electron, its possibility is more in an orbital of smaller size. And shape and orientation. Previously discussed the size, smaller size, that means finding of electrons has more probability near the nucleus. Then we'll consider now the orbital's shape and orientation. Shape and orientation, what it means? It means that there is a large probability of finding the electron along certain directions. That means shape and orientation, these two parameters of orbitals denotes some directions. Atomic orbitals are precisely distinguished by quantum numbers. That means from the quantum numbers, we can identify the size, shape, and orientation of atomic orbitals precisely. So each orbital is designated by 3 quantum numbers labeled as N. I already told N is the principal quantum number, L azimuthal quantum number, and ML, it is the magnetic quantum number. Especially now we will focus only on N and L. So principal quantum number N, it is a positive integer with value 1, 2, 3 in increasing order. Principal quantum number determines the size. I already discussed that principal number only determines the size of the orbital. And to large extent, we can say the energy of the orbital. That means principal quantum number is for the size and energy of a particular orbital. Example, for hydrogen atom, we know that hydrogen atom has 1 electron, single electron, and hydrogen-like species, that means helium, singly positive charge, lithium, doubly positive charge, etc. all has the single electron only. In that case, the energy and size of the orbital depends only on the principal quantum numbers N. What I already discussed in the second point. The principal quantum number also identifies the shell. We'll discuss about the shell just after this. Next slide. So with the increase of the value of the N, the number of the allowed orbitals increases and are given by the N square. That means for a particular value of the principal quantum number N, the number of the orbitals is N square. That means here you see that when N, its value is 1, then N square also 1 square, that means 1. That means for principal quantum number 1, the number of allowed orbitals is also 1. But when you consider the n is equal to 2, that means principal quantum number 2, in that case, the number of the allowed orbitals increased, that means 2 square is equal to 4. And similarly, when n is equal to 3, then number of allowed orbitals is 3 square, that means 9, and so on. All the orbitals of a given value of n constitute a single shell of atom and are represented by the following letters. N is equal to 1, 2, 3, 4. And the shell, actually, we denotes the capital letters K, L, M, N. And so the size of an orbital increases with the increase of the principal quantum number n. We know that with the increase of the principal quantum number n, the number of allowed orbitals also increase, and same way the shell also, its size will be increased. The number, that means the principal quantum number n, its increase, what does it mean? With the increase of the principal quantum number, the n value, the electron will be located away from the nucleus. And if you want that electron means it is the negatively charged, and you want to make it away from the nucleus is the positive charge. So it needs energy. That means with the increase of the principal quantum number n, the energy also will be increased. That means the energy related to the principal quantum number will also be increased. That means since energy is required in shifting away the negatively charged electron from the positively charged nucleus, the energy of the orbital will increase with increase of the principal quantum number n. Now we'll talk about azimuthal quantum number. Azimuthal quantum number we denote by L. I already discussed in the previous class also. And it is, what does it mean for azimuthal quantum number? It is the orbital angular momentum or subsidiary quantum number. It defines the shape. I already told that size defines by the principal quantum number, and this azimuthal quantum number L, it defines the three-dimensional shape of the orbitals. We have to always remember that principal quantum number is related to the size and azimuthal quantum number is related to the three-dimensional shape of the orbital. So for a given value of n, the L can have n values ranging from 0 to n minus 1. That is, that for a given value of n, the possible value of L are 0, 1, 2, up to n minus 1. So you consider here as an example that when n is equal to 1, then the possible value of L is only 0. That means n minus 1. 1 minus 1 is equal to 0. And when the n, the value of n is 2, and then what it will be 0, 1, that means 2 minus 1, n minus 1, that means 2 minus 1, that means it will have the two values. That means for a given value of n, L can have n values. That means if the value of n is 2, then L will be has two values, 0 and 1, and so on. That means with the increase of the value of the principal quantum number, then the value of the L also will be increased. So here what I already told, that example is there, and for n is equal to 3, the possible L value is the 0, 1, 2. This shell consists of one or more subshells or sublevels. That means this subshell and sublevels, it is related to the azimuthal quantum number. That's why the each shell means it related to the principal quantum number, and it has the sharp cells, number of sharp cells, which is based on the azimuthal quantum numbers. The number of sharp cells in a principal shell is equal to the value of n. Obviously, because principal quantum number, what is the principal quantum number? The value of the principal quantum number, if it is 2, then the sharp shell also will be 2, because azimuthal quantum numbers has the value 2. So this is very important statement. That means when the principal quantum number n is equal to 1, then obviously this shell has only one subshell. And when the principal quantum number is 2, then this shell has the sharp cells 2 numbers, and so on. So in this table, we'll find clearly about the number of sharp cells and their notations. So here you can see that n is equal to 1, then L is equal to 0, and then only one subshell is there, its notation is 1s. And when n is equal to 2, then subshell, that means based on the L, it is a 0, 1. That means subshell number is 2, one is denoted by 2s and another is denoted by 2p. Similarly, when n is equal to 3, then it has the L value 0, 1, 2, and accordingly the subshell 3 number of subshells, 3s, 3p, 3d. And when n is equal to 4, then you can see the L value is 0, 1, 2, 3. And in that case, the subshells notation, subshells also 4 numbers of subshells, and their notation is 4s, 4p, 4d, 4f. So with this, I hope that you understand very clearly that what is the relation between quantum numbers and orbitals, how quantum numbers determine the size and shape of an orbital in atoms.